So here we have a little simulation that we can use to sort of practice some of the ideas we were talking about with distance and speed and all that kind of stuff. So it's got a basic little guy up there, and he's sitting at 0 meters, a little reference point, and we can give him a little speed of 5 meters per second on the side over here. If we have him sort of just move along here, we can get the graphs actually created. You can see as he goes, moves along, and the graphs are actually drawn until, of course, he gets to the wall. And then we have something like this where he just sort of stays put. So if we sort of look at this a little bit, we got the basic DT graph here at the top, nice straight line, and it's a straight line, of course, because his speed is nice and constant. And what you guys are working with is DT graphs and stuff like that. So I mean, if this, here's your basic DT graph when a distance of 10 meters and it took 2 seconds. So really fast. So of course, 10 divided by 2, the slope of the line would be 5, right? Rise over run, you have 10 over 2. The speed would be 5, and that's why on the VT graph, there's a nice horizontal line at 5 meters per second all the way across. And then, of course, when he gets to the wall, his distance, of course, stays at the 10 meters, and this comes crashing down and just sits at 0 because he is at rest. Okay, so pretty straightforward. Of course, we could even change this a little bit. Let's just clear things up a little bit here. Put him back at the 0 location. We give him a speed of, let's say, 4, and we can do the exact same type of thing and sort of sketches it out, something like that. And it's the same idea. So this time, he did the 10 meters, and he did the 10 meters in just over 2.4 seconds, and you divide the 2 out and you will get, so it gets to be 2.5 seconds, divide the 2 out and you will get a V of 4, which is what we set it at, and that's why the graph is sitting here right across at 4. So it's just basic, simple linear motion. So now let's modify this a little bit. Motion isn't always nice and constant with constant speeds and stuff like that, and that's where acceleration starts kicking in. So now we're incorporating an acceleration graph. We brought the guy back to the beginning. Now let's incorporate some acceleration. Of course, when acceleration kicks in, we've got a few things going on. So let's just start with a nice little acceleration right there and get this guy to go. And we've got the graphs going, something like that. And of course, he hits the wall. Okay, all good. Now, we're not going to worry about the juddery stuff at the end, but there's a couple things here. First of all, since he's accelerating, if we look at the DT graph, it's now a curve, and that right there is a little bit different. So when you're accelerating, you get a curve in the DT graph. And you probably remember that a little bit from the kinematics you guys did in grade 10. Now, the interesting part for the velocity one is it's still a straight line. It looks a little wibbly wobbly, but it's still a straight line. But instead of being a horizontal straight line with a constant V, now it is slowly going up as a straight line. And that's because, of course, the speed keeps on increasing. And now you can actually find the slope of that line. If you found the slope of this line, it would give you the acceleration. Now, it's kind of hard to tell. I don't know if we can zoom in here a little bit. Oh, there we go. We can zoom in a little bit on our acceleration graph, because I had set the acceleration to 2. It's 0 because he hit the wall. But that line is straight across at 2. And if you found the slope of this VT line, the slope would be 2, because its rise over run for velocity will give the acceleration. So the same way the rise over run or the slope of a DT graph gives you the speed, the slope of a VT graph will give you the acceleration. And we start looking at things like acceleration. It's much more common to look at VT graphs than DT graphs, because straight lines are a lot easier to use than curves, which is what we have in the DT graph. So when we start looking at acceleration, we'll mostly be sticking with VT graphs because you get straight lines instead of curves, and it's just a little bit easier to work with. So that's what we're going to look at a little bit today, is what happens when you don't have a constant speed, you do have acceleration, and how to incorporate a couple things with that. So let's sort of go back to the types of things we were looking at before in terms of DT graphs. So this we're talking about, you get your basic DT graph that looks something like this. Okay, no big deal, and you guys already know this is a nice constant speed, and of course that is the slope. But when we don't have a constant v, we get the acceleration kicking in, it gets a little bit different and difficult sometimes. So I mean, you have something like this, right? This is not a constant v, right? So this is when we have an acceleration. That doesn't mean you can't do slope type stuff, but this is where what you would need to do, and we practiced before in the intro section, is when you have a curve or something like that, this is where the stuff that you guys did, stuff like this, where your tangents would kick in. So when you have curves and stuff like that, what you can do is, I mean, you can't find the slope of an entire curve, but what you can do is you can find the slope at a point. And of course, this is the tangent stuff we practiced in the intro unit. And you can find the instantaneous v, and it's often written as V-I-N-S-T. So you can find an instantaneous speed or an instantaneous velocity. You can do that instead. And you can define any point you want. So often, you know, if you have a curve or something like that, it won't ask you to find the speed. It might ask you to find the speed at 5 seconds or find the speed at 8 seconds. And then it means, is really implying that you want to make a tangent, find the slope of that tangent, and then you can get that speed at that point. But again, curves, you know, those are a little more difficult to analyze. So typically when we have acceleration, what we want to do is, instead of, you know, using a dt graph, we want to typically use a vt graph, because a nice steady curve like this would give you a nice straight line on a vt graph. And this is a lot easier. This is a lot easier to work with. Straight lines are a lot easier to work with than curves. So when we start talking about acceleration, we typically kick into a VT graph rather than a DT graph, just to make things easier to work with. And of course, we can do the same type of thing. The slope of this thing would be the change in v over the change in t, and of course that gives you the acceleration. So the same way a slope on a dt graph gives you the v, the slope on a vt graph gives you the acceleration. So it's all the same, similar type of idea. Okay, and you can get curves in VT graphs and get instantaneous accelerations as well. I mean, that's also relatively commonish type thing to happen, but that's more later on. We just worry about nice linear accelerations, constant accelerations for one section at a time. It works a little better. So we're going to practice a little bit and work with this a little bit, pretty much the exact same way we did the DT graphs, because really there isn't much difference between how everything sort of works. So let's just start by making a graph here, and we're going to like pretty much the exact same type of thing as when we introduced the speed and the distance time type stuff. I'm going to make a graph here, and I'm just going to make something up here, put some little ticks on here. Let's go 2, 4, 6, 8. Okay, so this is my time, and this is going to be my v. And I'll get some lines in here as well. And let's go up by 5, so got something like this. Okay, and I'm going to put some lines on here. All right, something like this. And then we'll go across just a little bit. And then, not perfectly straight, but close enough. And then I'll do one way out here. And we'll say they're all nice exact coordinates and that type of stuff. Okay, so with this, we've got a VT graph, and we are going to find, we're doing the same type of thing we did before. What are the accelerations? So what are the accelerations for the 3 parts? So, you know, part A, part B, part C. Same idea. All right, so A, B, and C. So if I'm looking for the accelerations, I'm just looking for the slopes, just like the DT stuff. So I want to find out what my slope is, which of course is my change in y, which is the change in v, over change in x, which of course is the change in t. So I just want my change in v over change in t for each section. So if I go with the first part A, it goes from 0 meters per second, and it goes up to 15. So the rise would be 15. And it went across to 4 seconds. So I just have to divide those two out, and I've got my acceleration. So we punch that out, and we get 3.75 meters per second squared. Okay. Then we go to section B. Now B is just going straight across for a couple seconds. So if it's flat, the slope is 0, and there'd be 0 acceleration at that point. We can go to C. We'll do the same type of thing for C. If we look at the change in V, it starts at 15 and it goes up to 25. So the change in V was 10, and that lasts for 8 seconds. So we've got 10 divided by 8, and of course 10 divided by 8 is going to give us 1.25 meters per second squared. So those would be the 3 accelerations for those points. Okay. Now, same type of thing as when you guys did with DT graphs. What is the average acceleration for the entire thing? Well, if I want the average acceleration for the entire thing, again, I'm not going to add up my 3 accelerations and divide by 3. That's not how this works. Same as what we did before. What I want to do is I want to look at my change in V and my change in T for the entire thing at the same time. So acceleration is change in V over change in T. So my change in V for the entire thing starts at 0 and it goes all the way up to 25. So 25, and the entire thing took 14 seconds, so 14 seconds. So I'll do the 25 divided by the 14, and we get about 1.79 meters per second squared would be the acceleration for the entire thing. Now, mathematically, if I would take a line and I go from beginning to end like this, the slope of that line would be 1.79 meters per second squared because it represents the change in V and the change in T for the entire thing. Okay, so that's sort of how that would kick in. All right, so that's how we can find the acceleration for this guy. All right, so now what if we try and incorporate the other stuff that you guys have done as well? What if I wanted to know how far it's gone during each section? So I want the distance for each section. Okay, well, you have one expression for distance, dTV. Okay, so you've got times for each section, you got V's for each section, so we got just piece things together. So if I go to the first part, just part A, and the time for the first part lasted 4 seconds. So I've got 4 seconds. Now the thing is, what V do I use for the first part? It starts at 0, it goes up to 15. Do I use the 0 or do I use the 15? Well, I'm actually not going to use either one of those. Now, dTV is based on the idea of having a constant speed. That V right there, this V, is supposed to be constant. But what if it's not constant? Well, if it's not constant, then you have to sort of treat it as a constant, which means you have to take the average V. And that's why you'll often see it written with a line on top because it means average. So I'm not going to use the 0. I'm not going to use the 15. My V during the first part went from 0 to 15. And the average of 0 and 15 is right in the middle at 7.5. So that's what I'm going to use. I went from 0 all the way up to 15 meters per second. Right in the middle would be 7.5. So I'm actually going to use 7.5 meters per second there to calculate my V. Okay, it's sort of like if you've got 2 marks on assignments. You got 50% on one assignment and you got 100% on the other assignment. The average of your 2 assignments would be 75. Well, there's no difference between getting a 50 and 100 and having an average of 75, and if you had gotten 75% on both of them to begin with, your average would still be 75. So when it's a changing in V like this, is what we do is we go to the in-between, right in between the 2, halfway in between, and take the average of the 2 values. So from 0 to 15, the average V would be 7.5. So I'm going to multiply the 4 by 7.5, and if I do that, I will get a distance of 30 meters. And that's how far it went during the first part. So now I'm going to go to the second part. When I go to the second part lasted for 2 seconds. And now I need the V for the second part. Now, during part B, is the V constant or is it changing? Well, it's constant. It's at 15 the entire time. So I don't need to worry about the average. It's just 15. It's straight across at 15. So this stays as 15 meters per second. So 2 times 15 is another 30 meters. Okay, so now I'm going to go to the last part. I'm going to go to part C. Now, part C lasts for 8 seconds. So I'm going to go 8 seconds. Now, is the V changing or is it constant? Well, it's changing, so I'm going to have to use the average. So it starts at 15 meters per second, and then it goes up all the way to here, which is 25 meters per second. So I have to use the average of 15 and 25, the halfway in between. Of course, the halfway in between would be the 20. So the average speed for that one, for part C, is 20 meters per second. So 8 seconds, average V of 20, that would give us 160 meters during the last part. So now all I have to do is take those three and add them together. So combine all three of these together, and we've got 220 meters was traveled altogether. Okay, so that's the basic idea behind how this stuff works and how it connects to what you guys have done previously. And hopefully you can see, like, organizing your stuff, labeling your stuff is going to be really, really, really important when you've got multiple parts. Okay, so let's do another one very similar to this and sort of see how things can fit together again. Okay, so I'm just going to draw another graph. I'm going to make something up again, another VT graph, something like this. We'll get some lines across the bottom here. And let's go with, let's go up by 10 seconds each time. There we go. And then 1, 2, 3, 4, 5, 6, 7. And I'm actually going to go up by 50s just for fun. There we go, something like that. Okay, so I'm going to draw some lines on here. I can use a different color. I'm going to draw a line from here to here, like that. Okay, and then let's draw another one going where is it? There it is. We'll draw another one going something like this. Actually, let's go all the way up here. There we go. Let's go way up here. And then I'm going to drop it all the way back down to the very end, something like that. Okay, so let's do the same type of thing that we did before. Okay, so I got 3 parts to it. Got part A, B, and C. And so we got A, B, C. And let's just start by finding what are the accelerations. And this is the exact same thing we just did. So we'll find the slopes of our 3 lines. Okay, so for the first one here, my change in V for the first part, and of course remember this is change in V over change in T. My change in V for the first part, it went from 100 up to 200, so it changed by 100. There's my rise, and that apparently took 20 seconds, so that would give me 5 meters per second squared for an acceleration. Okay, so we'll go to B. If I go to B, it starts at 200 and it goes up to 350. So the change was 150 because it goes from 200 up to 350. And that took 10 seconds. So that would just be 15 meters per second squared. And then if I go to the last part, it starts at 30. Oh, sorry, a little drink break. That's better. Okay, so for part C, we're starting at 350, and it goes all the way back down to the 0 for speed. So it went from 350 to 0. So the speed dropped by 350. So technically it's negative 350 because, of course, it's you're losing speed. And that took 30 seconds. I'm going to run out of room here a little bit. So if I do the 350 and I divide that by the 30, I will get an acceleration of, I'm going to write down here because I'm running out of room, negative 11.7 meters per second squared. Okay, so that's my acceleration for the last part. So, and you can just incorporate the negative at the end if you want. If you don't want to put the negative 350, it doesn't matter. You see it's going down, just toss the negative at the end if you want. Okay, so what's the average acceleration for the entire thing? Okay, so again, we're going to look at the entire situation from beginning to end. We don't care about the in-between. It's about beginning to end. So if I look at the change in V over change in T for the entire thing, well, my first V at the very beginning is 100. And then, I don't care about the middle, all I care about is the end. It ended up at 0 meters per second. So the change in V was minus 100, and that took 60 seconds. So if I just do that 100 and divide that by 60, I will get an acceleration of, and it's negative, 1.67 meters per second squared. Okay, and again, if I took a line and I joined it from beginning to end like this, the slope of that line would be negative 1.67 meters per second squared. So it's all the same type of thing. Okay, all right. Now let's do what we did before. Let's also find out the distances that were actually traveled. So what's the distance that was traveled? So I'm going to find 3 distances. All right, so of course, distance is, of course, dTV. So I'll do the same type of thing we did before. So I'm just going to go over to the first part. And during that first part, it lasted from 0 to 20 seconds. So my time is 20 seconds. And it's either constant V or average V. So do I have a constant V? No, I don't. So I need to use the average. So during the first part, it started at 100 meters per second and it went up to 200 meters per second. So the average would be right in the middle. So that would be 150. So I just need to punch that out. So I got the 150 and I times that by the 20 and we went 3,000 meters during just that first part. All right, so now I'll go to the second part. The second part lasted for 10 seconds. Do I have a constant V? No, so I got to use the average. So it went from 200 all the way up to 350. So the average of 200 and 350 would be 275. So right in the middle would be 275. So multiply, we got 2750 meters for the third part. And then we'll do the same thing for the last part. So last part lasted from 30 to 60 seconds. So it lasted for 30 seconds altogether. And if I want the V for that, is it constant? No, it's not constant. So I got to use the average. Well, it went from 350 all the way down to 0. So I just basically got to take that 350 and cut it in half. And if I cut it in half, I've got an average speed of 175. So then I'll just times that by my time of 30 seconds. And I've got about 5250 meters for the third part. So 3,000 for the first part, 2750 for the second part, and 5250 for the third part. So all I have to do is take those 3 and add them up. And if I do that, I will get 11,000 meters altogether. So that's how far this, whatever it is, happened to go during this time frame. Okay, so this is like the graphical way to look at VT graphs. So again, it's very, very, very similar to the DT graphs, just finding different quantity. But again, it's about finding slopes. But then we can incorporate the DTV stuff that you guys have done as well to find the distances. You just got to be careful with the constant or average. And I often just ask myself, is my V constant? No, then I'll find the average. If it is constant, then it's a lot easier. So next, we'll also practice this in more like traditional scenarios, just like we did with the DTV stuff. But we always like to start with the graphical stuff first.